Assalamualaikum warahmatullah. So today we are going to discuss about the approximation technique in spatial distribution. Okay, so there are three approximation technique that we will discuss. Poisson approximation to binomial, normal approximation to binomial, and also normal ascending approximation to Poisson. Okay, so basically we use approximation when we are not able to use the original distribution under certain condition, right? So when do we use the approximation? So this is the rule of thumb. Okay, if we meet this rule of thumb, we can use the approximation. Okay, so and basically the approximation is easier to conduct compared to the original distribution, or easier to calculate, right? So we use Poisson approximation to binomial when um, when the the number of trial is greater than 20, n is large, and the probability success P is small or less than 0.05. Okay, so under this condition, if we meet this condition, we can use the Poisson distribution instead of binomial. Okay, so the second one, normal approximation to binomial, meaning that the original distribution is binomial. So under certain condition, it is not suitable for us to use binomial. So we can use approximation, or we can use normal approximation. So this is the rule of thumb. If n times p greater than 5 and n times q greater than 5, we can use normal distribution instead of binomial, right? So to get this, n greater than 5, np greater than 5, and q greater than 5, this is given a large trial lah. Okay, the number of trial is large, so we will get np greater than 5 and nq is greater than 5. Okay, the third one, normal approximation to Poisson. Okay, meaning that the original distribution is Poisson. So if the lambda, is, or the average is greater than 20, we can use normal approximation. Okay, so we will go through this approximation one by one. The first one, Poisson as an approximation to the binomial. Okay, so from the original distribution, binomial, okay, so from binomial, we have the parameter n, p. Okay, binomial n, p. So when n is large, n greater than 20, and p is small, less than 0.05, we can use Poisson approximation. We can use Poisson instead of using the binomial distribution. Okay. For example, this is because if we use Poisson, it is easier for us to calculate, or it is it is possible for us to calculate it, right? So let's say we have n equal to 25. Okay, n equal to 25, p 0.01. Okay, so if you want to calculate the probability, let's say probability x greater than x less than or equal to 1. Okay, so f0 plus f1. Okay, so if you want to calculate the, if we substitute the parameter into the PDF, okay, NCX 25 C0 times 0.01 power of x and 0.99 power of 25. Okay. This uh, this value, the large N and also the small p, will lead us to a very small figure, okay, or it is uh, hard for us to calculate the probability, right? That's why we use approximation. We can use Poisson distribution. Right, so if you want to use the Poisson distribution, for Poisson, we need only one parameter, that is lambda. Okay, so in this case, lambda is equal to n times p. Okay, lambda equal to n times p. Okay, so we use the approximation. X is approximately distributed with Poisson, lambda equal to n times p, right? So the Poisson PDF will become fx. The original one is exponent negative lambda, lambda power of x over x factorial. Okay, so lambda here is equal to n times. Okay, so let's see an example. Okay, example one. Example one, we have accident occur, right? It is known that the probability of an accident on any given day is 0.005. So this is the P, right? P 0.005. What is the probability on any given period of 400 days? Okay, so we want to study for 400 days, meaning that 400 trial lah. This is n equal to 400. Will there be an accident? Okay, so kita nak calculate probability x equal to 1. Okay, because P is small, very small, and N also very large. Okay, so we can use Poisson approximation instead of using binomial. Okay, so the original distribution is binomial with n 400 and p 0.005. Okay, so now we want to use Poisson approximation. Lambda is equal to n times p. N times p, 400 times 0.005, we get equal to 2. Okay, so for question A, we want to calculate the probability x equal to 1. Okay, so we just use the Poisson PDF. Exponent negative lambda, lambda 2 times lambda power of x equal to 1 over x factorial. Okay, so the probability is equal to 0.2707. Question B, what is the probability that there are at most 3 days with an accident? So question B, we want to calculate probability at most 3. So x less than or equal to 3. equal to F0 plus F1 plus F2 plus F3. Okay, so this one we need to substitute one by one lah. To calculate one by one, x equal to 0, equal to 1 plus equal to 2 plus equal to 3. Okay. So exponent negative lambda, lambda power of x over x factorial plus lagi sampai 3 lah, 0 until 3 Exponent negative lambda, lambda power of x over x factorial. Okay, so you will get the answer is 0.8571. Right, for example 2, in a manufacturing process where glass products are produced, defects or troubles occur, right? Occasionally, okay, it is known that on average, 1 in every 1,000 items produced defective lah, right? 1 over 1,000 defective. What is the probability that a random sample of, okay, here I want to change this, random sample of 4,000 4,000 will yield fewer than 4. Okay, I just changed the question. Okay, so the original distribution is binomial with n, okay, n equal to 4,000, and p, the probability success is 1 over 1,000 or 0.001, okay, p. So because n is very large and p is also very small, we can use the Poisson approximation, lambda equal to n times p, 4,000 times 0.001. So lambda is equal to 4. Okay, so we want to calculate here the probability fewer than 4, so meaning that probability x less than 4. So F0 plus until F3 lah, plus F1 plus F2 plus F3. Okay, so exponent negative lambda, lambda power of x over x factorial plus exponent negative lambda, lambda power of x over x factorial plus exponent negative lambda, lambda power of x over x factorial plus lagi until x equal to 3. Okay. So just calculate this using your calculator and you will get the answer is equal to 0.4335, right? Okay, the next example is similar with example 1 and 2. Yeah, the original distribution is binomial, so because n is small and n is large and the p, the probability success is small, so we can use the approximation, the Poisson approximation. You can try this out later. Okay, for example 3, you will get the answer probability x less than 5 equal to 0.6288, right? And also The same with example 4. You can try this out later also, but I want to change this. The n we use 5,000. Okay, 5,000. P is 1 over 1,000. Okay, so probability at most 6 or x less than or equal to 6, you will get the answer is equal to 0.8201. Okay, so these two examples you can try it out by your own later, right? Okay, I want to proceed with the next approximation, normal approximation. Okay, so for normal approximation, we have to normal approximation to binomial and also normal approximation to Poisson, meaning that the original distribution is binomial or Poisson. Okay, under certain condition, we can use the approximation to normal. But before, if you want to use the normal approximation, we need to do a continuity correction first, because normal is a continuous distribution, okay, and Poisson and binomial is the discrete distribution, okay, meaning that the original distribution is discrete, okay, and then we want to do approximation, we want to use the normal is continuous, okay, from discrete to continuous. From discrete distribution, we want to use the continuous distribution to calculate the probability, okay, because the original one is discrete and we want to use the continuous, we need to do the continuity correction. Call it continuity correction. So this continuity correction depends on the sign of the probability that we want to find. Okay, so this is the continuity correction. If you want to find the probability x less than no equal, okay, we minus x minus 0.5. If less than and equal, plus 0.5. Greater than, plus 0.5, and greater than and equal, minus 0.5. Okay, so this one you need to remember lah, right? The continuity correction, whether to plus or minus 0.5. Okay. For example, let's say we want to find the probability x greater than or equal to 4. Okay, so greater than and equal to 4, we need to minus 0.5. So it will become probability x greater than or equal to 3.5. Okay, after this, baru kita convert the x to z. Right, so we need to do the continuity correction first. After that, baru kita calculate z. Right, so if x greater than 4, we need to plus 0.5, so it will become 4.5. If x equal, we must do both, okay, plus and minus 0.5. Okay. So if x equal to 4, we must do both, plus and minus. So 4 minus 0.5, 3.5, and 4 minus 4 plus 0.5, 4.5. Okay, so means we need to calculate the probability x between 3.5 and 4.5. Okay. X less than 4, we minus 0.5, so it will become x less than 3.5. X x greater less than or equal to 4 plus 0.5, so it will become 4.5. Okay. So the first one, normal approximation to binomial, we can use this when NP greater than 5 and N times Q greater than 5. Okay, so the original